This is a really cool idea. This is one of the things they don't really cover. And this is why there can be mismatched base pairing in DNA. If you can't get it, the whole idea is, I don't even know how to draw something on the root structure. So let's say this is adenine, right? This is our two ring, really ugly looking. And it has two hydrogen bonding potentials, and it can usually bond with thymine. And cytosine is also pyrimidine, but it doesn't match up with adenine, which is a purine, because it has 3 hydrogen bonding, so they don't align. But the cytosine can be tautomerized by, like, UV light might cause it to isomerize into a different structure, just by the way the double bonds rotate and adding a hydrogen, so that now it will have 2 hydrogen bonding potentials. So now A and C can align up with each other.
Oh.
So then, and it fits. They fit puzzle pieces. Now, the thing is, if it tautomerizes back to its normal structure, then the cytosine won't hydrogen bond properly with the adenine, and so then it will bulk out. And so then the cell can recognize it. But if the cell doesn't catch that in time, and the way the cell knows it is one strand of DNA, and this is getting more to replication, which we're going to talk about later. One strand of DNA is methylated. The new incoming strand doesn't have methyls on it. But if that doesn't tautomerize back to its original structure, and it gets methylated, and then it tautomerizes after it's methylated, then it's going to be a mutation. The cell won't know which base pair was the wrong structure, if that makes sense.
Yeah, that makes sense. So it's like a way that mutations occur without, like, the body catching on type of thing.
Yeah, and most of them do, because it, like, UV light causes it, and it's going to tautomerize quick enough that.
This is right, like with the enzyme nucleic acids 5' to 3'.
Yeah, 5' always on the left.
Okay. I can just do that because it has on the slides. So I wrote a bunch of stuff like this anti-parallel area about, like, the base pair occupy the same area, but, like, the structure, like the bonds aren't actually directly opposite of each other. They're, like, kind of a thing. But was that part of that, or was that actually part of the major minor groove?
Major minor groove.
Okay. So because I, like, was writing a bunch of stuff and I was like, he's like, and this is what makes the major minor groove, and I was like, oh, well, never mind.
Yeah. And then the phosphodiester bond is just the phosphate linked with, and that's super easy. Okay, you have like a phosphate here, then down here. On the 3' end, you have a hydroxyl. These come together, and you get a water off.
And you just get, like...
And so they're linked right there.
Okay. And so, and it always happens with, like, the first phosphate and the other two just kind of get dropped with it?
Yeah, because usually when DNA comes in, like, it has a triphosphate.
So
then, yeah, 2 phosphates leave, and 1 phosphate forms the bond.
Okay.
You see the mechanism? Okay, yeah.
It's right here.
Spontaneous rearrangement. So they're showing you how, which one is which? Oh, they're showing you C on the left here, how it can go from C and then it can tautomerize to form this different structure of C. So normally C will form 3 hydrogen bonds, but now it's only going to form 2. So now it can line up with adenine to form 2.
Oh, I see that.
Or here they're showing you how adenine tautomerizes to form a different structure that will line up with cytosine.
Okay, and these are just happening, you said, like, this, like, UV light, like, just some sort of thing that causes the mutation?
Yeah, and so if cytosine were to tautomerize back, then you could see they wouldn't be lined up, and so then that would prevent it from being able to hydrogen bond, and so then it would
Follow them.
recognize that there's
Okay.
a placement of a base
And
pair.
then at that point, it just kind of comes in and like
Yeah,
destroys
I will
it.
remove it, and you'll learn how your exonuclease works.
Okay, so basically, in essence, what, like, this question, like, I guess the overall thing is that, these bases can change to form different type of hydrogen bondings, but then if it changes back to its native or like original like state, then it can be seen as like a mutation and be recognized by the body.
It will, no matter what, it probably eventually will go back
Okay.
to its native form. But it's either, you'll either get removed in DNA synthesis, or if it's too late, and that's what causes a mutation.